Hopefully it stays that way. My name is Alberto. I work at Moonbeam, and today we're going to talk a little bit about Moonbeam and XCM. So I have a lot of content, so it might be just our experience, and we have time. It will be what's to come. It just depends on how much time I have left. But yeah. I personally have been engaging with XCM for over a year, almost a year, and it's definitely a tough thing to get to know and to work with. I am not a developer. I only do developer relations, and so this is sort of like a more high-level scope of what XCM is and the tooling that we've built around XCM. And we wanted to share it with teams building parachains and teams building dapps around XCM because we feel that it's important to share this knowledge that we've gained in over a year of experience. So, wow, that's bright. So today, I'm going to start with a little overview about XCM. Like, we're going to talk about instructions. What are they really quickly? We're also going to talk a little bit about execution of XCM instructions. And we're going to talk also about XCM fees, because it's a topic that there's not a lot of documentation on, but it's important because you want to know how much it's going to cost you to execute an XCM call, right? Then we're going to also talk about XCM tools that we've built around our XCM experience, right? So we're going to talk about monitors and also a GitHub repo that we use quite often to debug XCM stuff. If we have time, and this is what I mean that I'm not sure, we're going to briefly talk about the Moonbeam SDK. Either way, you can find us and contact us through our channels if you want to learn more, and I'll have the QR code of the presentation if we want to see those slides. And last but not least, what's to come on Moonbeam and XCM, which is mainly remote EVM calls through XCM. Actually, I was doing a demo of that earlier today, but this is pretty exciting stuff that we're working on. But let's first go to XCM overview, right? I think a lot have been said on this Sub0 conference about XCM, but basically, XCM is a language for consensus to communicate with each other, right? The way that I like to see it is a set of instructions that when they're executed, they result in a given action, right? It's like my mom telling me, get up, go there and flick the switch, and then my brain, which is the XCM VM, will actually understand those instructions and execute them. And it's important to understand that a combination of these instructions is that we actually do certain actions, right? If we want to do a token transfers, we'll use a set of instructions. If we want to do a remote transact, we'll do another set of instructions. And it's the combination which actually result in something being done. It's not only one instruction. In a typical sort of Polkadot layout, we have the relay chain, we have Moonbeam, we have other parachains, and there's certain communication channels that are needed to use XCM around, right? And these communication channels are unidirectional, meaning that if a parachain wants to communicate with Moonbeam, there's a one-way channel, and if you want to send a message back, there's another channel that needs to be opened. And these channels have tags or names. If you're talking from Moonbeam or a parachain to the relay chain, it's UMP. The other way around is DMP. And then between parachains, we have XCMP, but their current implementation is called HRMP. So let's go to one example of a typical interaction that is happening today, probably daily, on Polkadot, which is it's called remote token transfers, right? We have Alice, that it's an account on Polkadot. She wants to do a transfer to another account on Moonbeam called Alice. She can be the owner, or it can be a totally different person. And so there are certain XCM instructions that are executed on the Polkadot side, and there's certain XCM instructions that are executed on the Moonbeam side. But let's stay first high level, and then we'll go into a more lower level detail of these instructions. So through the XCM instructions, Alice is going to send her dots to an account, and a special account called a sovereign account. All right? And it has to be through an XCM instruction, because if she just does a regular balance transfer, it'll be like a very nice donation to the Moonbeam sovereign account, right? It's not the same, and it's really important. And what's going to happen is that throughout that XCM execution, there's going to be a message, an XCM message sent to Moonbeam that are 4 instructions, which the end result is going to be that some new tokens are going to be minted called XC dots on the account that Alice said that she wanted to send it to, all right? So before we go into more detail, let's talk a little bit about the sovereign account. And so the sovereign account, it's an account owned by an entire chain. It's a keyless account that has no real person owning it. And the only way to act on behalf is through different dispatchables and extrinsics and so on. But it's owned by a relay chain or the parachain on the different participants of the network. It is used to dispatch as a dispatch origin, and it holds funds. And if you're familiar with how Ethereum bridges work, like the locking and minting mechanisms, the analogy that I like to give here is like the locking smart contract on the origin chain where you keep the funds securely. This is a lot better though because there's basically it's owned by the protocol itself and not by just some logic there in the smart contract. And the address is deterministic, meaning that Moonbeam has an address that can be calculated, and this is how you can calculate it. It's not really relevant for the presentation, but Moonbeam has a sovereign account address on other chains, and the relay chain has also a sovereign address on the other chains as well. So if you go back to our example, and this is for whatever reason is flickering a little bit, hopefully it's not too destructive, but if you go back to our example, right, we have Alice sending dots to Moonbeam, and the sovereign account will hold these dots in the meantime, right? And so this is the instruction that gets executed on Polkadot, and this instruction, what it does is basically take funds from Alice, deposit it to the Moonbeam sovereign account, and it's going to send an XCM message that is going to start with 2 instructions for security, all right, which are reserve asset deposited and clear origin, and then the palette implementation that uses XCM needs to append the other instructions that are needed for the token transfer to be successful, right? This XCM instruction is not expecting that it's going to do everything, so the palette implementation needs to ensure that this is going to happen. And I'm going to leave a lot of URLs on the slides because we don't have time to cover everything, but you can click on it if you're interested in learning a little bit more. And if we go into the code of what happens when this this instruction is executed, there's a lot of line of codes here, but I want you to focus on this following lines, right? And remember that I mentioned that the instruction is going to transfer the funds from Alice to the sovereign account. And this is basically this line of code right here. It's easy to read. It's transfer asset, the origin, and the destination. And then I mentioned that we're going to send an XCM message to a destination chain that is going to start with 2 more instructions, right? And this is happening right here. We're preparing I don't know how to write Rust, by the way, but this can be read, right? I mean, you have an XCM message that has reserve asset deposited as the first instruction, clear origin as the second, and then you send that XCM message with whatever other instructions that were passed on to the instruction in the input, all right? When the XCM messages gets to Moonbeam, it should contain at least these 4 instructions. And the combination of these instructions is what actually ends up minting the XC dots, or the representation asset, to Alice's account, or Aleph account in this case. The first one is called reserve asset deposited, and this actually mints the token themselves, the XC dots, but keeps it in a special state called holding register, right? And the way that I like to see it is like you put money on the table and you leave it on the table so that it can be used for something else. The only person that can mint XC dots is Polkadot sovereign account, all right? So that's why the dispatch origin needs to be Polkadot sovereign account. But then the next instruction will remove that origin and say, OK, I don't want to do anything else on behalf of the Polkadot sovereign account, so I'm going to remove that information. The next one is going to buy some execution time on the destination blockchain, in this case, Moonbeam. I need to buy some block space so I can actually execute whatever I want to execute. And the last instruction is we're actually going to take the money on the table and then put it into Aleph's account, right? Something that I forgot to say is that basically the execution on Moonbeam, we can buy it from the holding token, so the token that is being held in the holding state, right? So for example, that's why you send 1 dot and you get 0.99 dots, because you're paying for that execution with the dots that you're sending. Like I said, all these URLs will take you to the same code that I showed before, so you can check for yourself the Rust code, just how this is done basically on the execution itself. So I'm going to jump between topics, right? And now we're going to talk about XCM fees. And as I said before, this is a topic that there's not a lot of information out there. And so if you want to actually read more, I suggest you go to our doc site. We do have a page with a lot more detail about how XCM fees are calculated, OK? But in order to talk about XCM fees, we need to understand what weight is. And I think Gavin mentioned it in its talk. But the way that I like to see it is sort of, it's basically the time that it takes to execute a given intrinsic in picoseconds with the standard hardware, right? So if we want to do a balance transfer with a Intel Pentium 3 or whatever, that's going to take a certain amount of picoseconds, that its weight. For XCM, there's, and this is only XCM, right? So this is very dangerous to say this, and also there's another error on this slide. But basically for XCM, you can say there is a weight to fee coefficient, right? So when you know how much weight that XCM execution is going to cost, you can multiply it by a coefficient, and you'll get the fee that you have to pay. This is only true for XCM because regular extrinsics have like a block, how much the block is full and so on. And so this doesn't work for all the extrinsics. Please don't use it. The other error here is to say that it's 0.11 Planck dots. I mean, there's no decimals of Planck dots. That's the smallest unit. But just bear with me in this case. And basically, you can see that I explain here how the coefficient is calculated. But if you're more curious, you can visit our doc site. But you can see that for Polkadot, they charge 0.11 something dots per weight for XCM stuff. And that's true also for Kusama. And then on Moonbeam and Moonriver, we have other coefficients as well. And so basically, once you have the weight and you have the fee coefficient, you can multiply them, and then you get the actual cost of the execution, right? So what I did here is that I brought some typical instructions, right? And for example, withdraw asset is used to send dots back from Moonbeam to Polkadot. And you can see that in Polkadot, they charge 1 billion weight units only for that instruction, right? Withdraw asset takes 1 billion picoseconds to execute. And if you multiply it by the constant that I just mentioned, this is the amount of dots that represents. I also brought an example for Kusama. You can see that these numbers, they are a little different than Polkadot. And this is because on Polkadot, they have not measured how much time it actually takes to execute that instruction. So they just say, I think 1 billion is enough. It's a conservative number, so we'll just use that, right? On Kusama, they actually did measure it, and that's why you have a more narrowed down number of the actual thing. On Moonbeam, we have not benchmarked these instructions, and so we have a little bit lower number than Polkadot, but it's still an approximation, right? So if you're interested in knowing how do we get this number, 145 millions. The way that you do this is basically you need to know, this is by the way another URL if you want to check it in more detail, but if you go to where the XCM benchmarking is done on Kusama, you will actually find this line of code where you see basically the baseline weight, and then you can read here that that instruction needs 1 database read and 1 database write. And if you check the weight numbers for RocksDB, each read takes 25 million weight units, and each database write takes 100 million weight units. So if you do the math, that's a total weight. And if you use the fee coefficient that I've mentioned before, you will calculate the cost of that in KSM of that XCM instruction. For by execution, for example, there is no database read and write, so it's only the baseline cost, and it's a little bit more straightforward to calculate it. So I brought some examples, right? I'm talking about numbers, but is this actually a representation of the truth? So remember that the fee coefficient on Polkadot is that amount. I put a warning because there's no decimals, but just bear with me. For this particular set of instructions, the weight is 4 billion, and this is the calculated XCM fee that I estimated just by doing a multiplication. And then we have more data like the total cost in Planck dot and so on. So I went to Polkadot, and I actually looked in Polkadot.js for a user that transferred 100 XC dots from Moonbeam to Polkadot, and the user received 99.95 something dots. And if you do the math, these numbers do check out, right? So the math is actually, it corresponds to the reality. And if you click on there, you will actually see the blog where this happened if you want to verify it yourself. The same is true for Kusama. I'm not going to go through the example, but it's fairly similar. Now we have the benchmark weights, which are different for each instruction. So the math is a little bit harder to do and just takes more time. And once again, I have an example that you can check on the URL where you can see that the fee is actually 0.0000 KSM, and that corresponds to the number that I pre-calculated before. So you actually, as a wallet, as a dApp developer, you can actually estimate in advance how much it's going to cost for that user to sign that extrinsic, and so on. On Moonbeam, it's a little bit different, even though it's similar because you can actually pay for XCM execution using other tokens, right? So if you're paying for XCM execution using Glimmer or Mover, there's basically a constant between Glimmer and weight. Or in this case, it's way to weight, which is hard to pronounce. But if you want to pay for, if you're sending an XCM message from Polkadot to Moonbeam sending dots, the way that we charge in that case is basically we say, for whatever reason, we decided to map it to 2 cents. So basically, when you send 1 dot, we're going to charge, or the network is going to charge roughly 2 cents of a dollar. Price fluctuates quite a lot, so this number has to be periodically updated. But the idea is that this is the amount of units of dots that we're charging for 1 second of execution time. But we know that it doesn't take 1 second to execute that XCM transfer, so it's a lot less. So you do the math. Basically, it's 800 million, 0.008 seconds. If you do the math, it just basically you can calculate how much it costs. Once again, I provided some real-world examples in case you want to check them out. But a user basically sent 1 glimmer to Moonbeam. This is actually from another network. I think it was either A-Star or Akala. And basically, the user received in Moonbeam 0.996, which basically checks out with the pre-calculated fee that I showed before. And for a user that sent 1 dot to Moonbeam, is it to, yeah, exactly, from Polkadot to Moonbeam, the user receives 0.99 something, which lines up with whatever I put before. And you have the URLs in case you want to check it yourself. So let's jump to another topic. And we're moving around because we've learned quite a lot, and I had to summarize it in 45 minutes. So we're going to talk about what multi-locations are. And multi-locations are super, super important because it's a way to represent something in a network as complex as Polkadot when you have multiple parachains, multiple users, multiple palettes and tokens everywhere, right? And there's one element that you can represent anything, and it's called multi-locations. So the way that, the person that, explained me a little bit about, to me, how multi-locations works is that I think a good analogy is thinking about folder paths. And you can actually define a target from a folder, right? Let's say you're in the documents folder and you want to go to the pictures folder. There's a way you can represent how you go from one to the other with the dot, dot, slash, blah, 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 right? And important that multi-locations are easier to understand if you actually express them relative to an origin. I'm in the documents folder. I want to go to the pictures folder. And like I said before, you can define anything. You can define a parachain. You can define an account on the relay chain, a token. And they contain 2 main things. A parent, that the way that I like to see this is how many hops are you going to an upper folder. Like if you're going from a parachain to the relay chain, you're going 1 level up, so the parents will be 1. And the interior is the amount of fields or the content to define what are you looking at in that specific folder. So I brought an example, right? Let's say we're standing in Polkadot, so our origin is on Polkadot, and we want to define how an account on Polkadot looks like as a multi-location, so Bob. So Bob will be parent 0 because we're standing in the same folder, and then we only need 1 field called x1 to define the account itself, which is an account ID 32 because Polkadot uses 32 bytes accounts as their account system. If we want to, from Polkadot, if we want to target another parachain, as an example, I put Akala, we need to only specify 1 field. So parents is still 0 because we're actually moving to an inner folder. And we only need 1 field called interior x1, and then we need to provide the parachain ID. If inside Akala, we want to target Alice, which is an account inside the parachain, we need now 2 fields because we need to tell the multi-location that we're going to Akala, and then we need to tell it to target a specific account inside Akala. For Moonbeam, it's very similar. So in the case of going to Moonbeam, we just provide the Moonbeam parachain ID. In the case of targeting an account inside Moonbeam, we need to specify the parachain ID and also the account ID 20 because Moonbeam uses Ethereum-style accounts, which are 20 bytes. And let's say we want to target a token inside Moonbeam, Albert token, right? That's the most famous token ever. And so basically what we need to do is in the multi-location define 3 things. We need to say the parachain ID because we're going into Moonbeam. We need to define the palette instance, which is the palette that handles this token itself. And then we need to define, in the case of Moonbeam, the general index, which is basically the asset ID. One important thing is that each parachain can decide how they represent their own assets, right? This is not a universal law, meaning that whatever Moonbeam is using, it's going to be the same in Hydra, in Akala, in Parallel, whatever. Each chain will have their own way to represent assets, and that's very important to understand. So very quickly, if we change the origin, and the origin is now Moonbeam, and we want to target Bob, we want to target Aleph. Now it's a little bit different because we don't have to specify the parachain ID because we're already in Moonbeam. So we only need to specify X1, the account ID 20. The same goes for the Albert token, right? We don't need to specify the parachain ID in Albert token. If we want to specify Bob from Moonbeam, we just have to say the same as before, but we need to put parents 1 because we're in the Moonbeam folder and we want to go to the upper directory. So we need to put parents 1. If we want to target Akala or Alice, it's the same as before, but because we're going through the relay chain, so we have to go 1 folder up to go 1 folder down. We need to make sure that we put parents 1, and that's the main difference between this example and the example before. Keep this in mind because later on we're going to show some examples that are using multi-locations. So for me personally, this is like the part that excites me the most about today's presentation because there's a couple of tools that we wanted to show you that has been crucial in sort of our XCM roadmap, right? And the first one is monitors. So monitors, before we go into the details of monitors, I want to make sure that we sort of refresh a little bit what I mentioned before about remote transfers, right? So Alice wants to take dots from Polkadot to Moonbeam. And so what Alice does is through XCM, remember, she's going to transfer some dots to the sovereign account. And so if you think about what this means is that on Moonbeam, there has to be at least 1 dot for each dot that the Moonbeam sovereign account holds, right? The Moonbeam sovereign account can hold more dots, so it can have 10. But this means that the maximum amount of XC dots that must exist, it's 10. It cannot be more if this is a 1-to-1 min ratio, right? If Moonbeam decides per dot that we get, we're going to do 2 dots, that's fine as long as they keep it on the way back. That's fine. But it's important that this ratio is matched. So if you think about this, and we say that it's a 1-to-1 mapping, the balance of the sovereign account has to be equal or greater to the total supply of XC dots. And that's a rule that cannot be broken ever. So we develop, boom, there you go. So we develop a monitor that basically says what I just said before. The sovereign account must hold at least the same amount of tokens that exist on the destination chain if there's a 1-to-1 ratio. And when we open XCM channels with other teams and so on, we actually create monitors that are monitoring these balances because it's important that the rule that I mentioned before is kept. And so on Moonriver, we have a total of 24 monitors. 17 monitors are checking these balances between the Moonbeam sovereign account and the other tokens. And 7 monitors are monitoring the mover balance between the sovereign accounts and other sites and mover. And we have 16 monitors on Moonbeam, 11 for external tokens, and 5 for Glimmer monitors, right? So as an example, we monitor our Moonbeam sovereign account on other chains, as well as other chains' sovereign accounts on Moonbeam. So for example, for A-star, Moonbeam sovereign account, A-star balance in A-star, right? If you remember the other diagram that I showed before, versus a total supply of XC A-star on Moonbeam. And a similar for the A-star sovereign account Glimmer balance in Moonbeam versus a total supply of XC Glimmer, I'm not sure how they name it, in A-star, all right? It's very important to understand that concept. And so to explain how our monitors work, let's go back to the remote transfer example. And I created this plot here that represents the difference between the sovereign account balance and the actual total supply of the token in the other chain. If it's positive, it means that all is good. Everything is great because we have more tokens than we actually have minted on the other side. And if all the users and the destination chain want to withdraw at the same time, they're going to get their tokens back. Everything is good. If the balance difference is negative, this means that it's bad, and that's why there's a sad face there, because it means that if for whatever reason all the token holders want to go back, they're not going to get the 1-to-1 ratio, right? Because there's not enough tokens on the sovereign account to fund those withdrawals. So the first thing that happens in our monitors is that we have a trigger condition, an alert condition that triggers a trigger condition that it basically, as I said before, if the balance of the sovereign account is less than the monitor, will trigger. But this would not actually alert us, the team, saying, hey, buddy, check this out, there's something going on. That happens if this condition is not resolved within 15 minutes. That is when we get an alert in our internal monitoring system saying, check this out, there's something weird going on, please review it. And the third thing is that resolution condition. If the trigger or alert is resolved for at least 30 seconds, the monitor will say, everything is good, buddy, go back to sleep or go back to work or whatever. All right? And you might think that this is overly paranoid and this has never been used in the history of Moonbeam and Moonriver, but we have at least had 3 incidents if I remember correctly. So I wanted to take you through some of them, right? And I'm not going to mention teams or anything, I'm just going to mention how the event went through, basically, right? So once again, this is the balance difference. Positive is all good. 0, it's fine as well. But negative, it's bad, right? And the time window here is roughly 20 to 21 hours. So there was a moment in time when there was an alert condition. We didn't hear anything because remember that we hear something when the trigger condition, and we didn't hear anything because we get a notification when the alert condition is activated. So we contacted the team and we explained the situation and they started looking into it, but you can see that the balance went up and down, but it never resolved. It was not more than 30 seconds, right? So after a lengthy period of around 20 hours, the monitor was able to resolve itself, but quickly there was another trigger, another alert, and an immediate resolution. However, the monitoring tool actually helped us solve this issue, the imbalance with Mover, in roughly 20 hours. I'm not sure what would have happened if this monitor was not in place, because who is actually looking at that, right? Another case happened on August 2022 with Glimmer, with a Glimmer imbalance, meaning that the sovereign account on Moonbeam was holding less Glimmers than the total Glimmers that were minted in that specific chain. Once again, there was actually a trigger condition that got automatically resolved, and so we didn't hear anything. But immediately after that, there was a trigger condition that resulted in an alert. We notified the team right away, and they were able to quickly solve it. For sure, these are implementation errors. These are issues with XCM implementation and so on. But then there was another trigger and another alert that was once again resolved by the team, but then there was another trigger, another alert that was actually resolved by the team, and they found sort of the problem, and so basically the monitor never triggered again. In this case, we were able to solve this imbalance issue within, I think, 3.5 hours. So think about, I mean, even though the balance difference is really, really small, think about what this means, right? If at any point in time, all the users are trying to withdraw these funds, they're not going to be able to, and there's going to be bigger problems if that happens, right? So this is a practice that we truly recommend to all the parachain teams that have channels with Moonbeam and with other teams to make sure that you can monitor these balances, because it's really, really important to set up these things. The other really cool tool that I have, it's a GitHub repo that you can find in the PureStake repo called XCM Tools, and I'll have the URL in the next slide. But it's a combination of tools that, don't worry, I'm not going to go through all of them because they're actually more than 6, but I did want to at least mention the first 3. And you can find the URL in the top right corner. But the first script I would say that I wanted to show you guys is a script to handle all the HRMP actions for channels, right? You want to open a channel to XYZ parachain, you want to open a channel with another parachain, or you want to accept the request and so on. And it's a set of scripts really easy to build, to use, that will provide the encoded call data and so on. You have also the generic call proposer, which actually helps you. It's not related to XCM, but we use it mainly for XCM. And it's able to create democracy proposals of encoded call data. You can use it either with a single call data or a batch call data. And the last one that is probably the one that I use almost on a daily basis is called Decode XCM messages, that it helps you to decode XCM messages, either if they're UMP, DMP, or HRMP, or well, HRMP. I mentioned this because if you think about it, and I think this has been mentioned multiple times throughout Sub0, there's no real way to debug XCM, right? I mean, you send an XCM message, it failed on the other side, and you're like, what can I do now? Like, there's no real way to understanding what's happening, unless you have tools like this that allow you to see what were the instructions that target parachain received, and you can actually start debugging after you know the instructions. So, but let's first start with the HRMP channels one, right? So I brought an example here. This is the actual code that we use to open the channel with statement. So you can see here that the action, HRMP action, is open. You provide the parachain ID WebSocket, sorry, the parachain WebSocket, the relay WebSocket endpoint, capacity, message size, target parachain ID, and you can even provide, if you want, the private key just to sign the transaction if it's a democracy proposal. You can actually do it also for counsel. You can actually schedule it for a specific block. You have multiple tools available at your disposal to use these tools. If you don't feel comfortable, putting your private key there, you can get the encoded call data and then go to Polkadot.js apps or whatever, and then just use it there. It's a tool that you can use for multiple things. This is another example that we use to actually accept the statement channel, so from statement to Moonbeam. And you can see that it changes a little bit because you have the HRMP action accept. If you actually go to the GitHub repo, we have a couple of MD files with all the times that we actually run this code in production. We put it there just in case, we want to make sure that we don't go back and subscan and check where this happened and so on. We have it there so we can remember what snippet we actually ran. The second tool is the generic call proposer. Like I said, this is not really XCM specific, but we use it, and I think we just keep it there. So it's very nifty because what you can do is that you run generic call propose, the WebSocket endpoint of the parachain or chain that you want to use it with. You can use it with the relay chain as well. And then you just provide the encoded call data of the different things that you want to batch in a single democracy proposal. So in this particular case, this is when we actually interacted to accept the channel with Akala. And so basically the first thing in blue is the accept encoded call data that we actually generated using the script that I showed before. The thing in pink, or whatever the call looks like, it's the part to open the channel with Akala. This next bit is to register the ACA asset, and this other bit is to register AUSD. So I mean, these other blobs of bytes we actually got from another tool that we have, but it's more Moonbeam specific because it's the way that we register assets and so on. If it's helpful, it is on the repo as well. And once again, this has all these different extra flags that you can use to sort of like manipulate this sort of proposal stuff. If you want to send it, you can provide a private key. You can schedule it. If you want to send a pre-image hash, you can do it. If you want to send a proposal, you can do it, and so on. Last but not least, this is probably the tool that I use on a daily basis, like I said before. It's a tool to decode XCM messages, right? So this is more or less how you would use it. You would provide the WebSocket endpoint of the destination chain, so the chain that received the XCM message. You have to provide the block where the XCM message was received, the type of channel, in this case is HRMP because it was sent from another parachain, and the parachain ID, in this case it was 2000 because it was a message from Akala. Here is another example to decode a message that was received by the relay chain. One really important thing, and I think I was talking with a guy from Hydra before, is that when you actually see the event that the XCM was executed on the relay chain, that is not where the XCM was received. It was actually on the block before. So when you use this code snippet, you have to put the block where the XCM was received, because if not, it's not going to show you anything. All right, and that's very important. And the last one is another example from an EMP, so a message that was sent from the relay chain to the parachain. You have here all the different sort of things, and one really cool thing that I'm going to show is that this supports XCM fragments, meaning that when you send two XCM messages on the same block, they're actually concatenated, one behind the other one. And so this tool actually supports this, and it will print the different XCM fragments, and that's actually helpful to debug an issue that we had. But why this is important? Like I said before, you send an XCM message, and in this case, for example, well, this is really bright. You can see that the message failed, and if you go to look at the message, it's just a bunch of bytes. Unless you understand that, which I don't think you do, it's really hard to debug what happened with the XCM message, right? So you can use these tools to actually decode the instructions and have sort of like a an easier way to actually check what happened, right? So to show you this, I brought some real-world examples that helped us to understand different problems that happened with different XCM messages. And I can probably have could have brought like 10, but I brought 3 different ones. So in this case, it was a message that was sent from Akala to Moonbeam. This is the block where it happened. You can actually just copy this and run it if you clone the repo and install the dependencies. As you can see, the error was basically the asset not found. We more or less guessed what was the error, but it's easier just to run the script and see what happened, right? So when you run it, you're going to get something like this. The first thing that it's going to show you is the hash of the message. That way you can match, right? I mean, you can see, OK, so this is actually the message where the error happened. The next thing is it's going to get all the instructions without the content of the instructions. So in this case, it's 5 instructions: withdraw asset, buy execution, transact, refund surplus, and deposit asset. And then it's going to print instruction per instruction with the content, the actual content, OK? In this case, once we saw this, it was pretty straightforward because they were trying to withdraw Glimmer. And actually, Glimmer is seen with not like this, not with this multi-location, which is parent 0 interior here, but parent 0 interior palette instance 10. I think it's 10, yeah. And so basically, Moonbeam does not understand this multi-location for Glimmer, and it's telling you, hey, buddy, I don't know what asset are you trying to tell me. I don't really understand it. But try to imagine doing this without this tool. I mean, you could still do it, but it's because you could go to Akala and see what XCM message they sent, but it's not always the case. The second example happened to me when I was doing some tests. I mean, similar to the demo that I did earlier on, I was sending a message from the relay chain that we have in our testnet to Moonbase Alpha, and I hit the barrier filter. If you're not familiar with barriers, basically, you can actually sort of whitelist the combination of XCM instructions that you're allowing in your parachain, right? Because I think there are, I don't know, 15 plus instructions. Imagine you would say, oh yeah, I want to block this particular combination, right? The combinations are endless. So it's easier just to say, I want to accept all these combinations or these particular ones. If not, if it's a combination that is not accepted, you're going to get the barrier filter. And so once again, to understand why this was happening, I ran the script, Decode para with the block and the channel DMP and the WebSocket. And the moment that I saw this, it took me like 1 second to understand what I was doing wrong, because as you can see here, we have 2 descent origin instructions, right? And when I was crafting the message on the relay chain, I was doing it manually, like adding the instruction 1 per 1 on Polkadot.js apps and so on. I was actually adding the descent origin instruction myself. But if you look at the XCM palette implementation that it's on the relay chain, they actually inject that instruction as well. So that's why you have it 2 times, and that is not something that Moonbeam likes. Moonbeam only likes it if it's 1 time. So basically, the barrier that we have set up is like, OK, descent origin. The next one has to be withdraw asset. But in this case, it's like descent origin. The next one is descent origin. I don't like that. I'm going to send a barrier filter. And so, with this tool, like I said before, I could quickly just check this out and fix my XCM, like the crafted XCM that I did, just to adapt it. And after this, the message went through. But you have also all the details about the descent origin and so on. The last example that I have here for you is another message that was sent from Bifrost to Moonriver. Actually, there's a typo there. It's HRMP. But you can see the parachain ID 2001. And this is a particular one because it's the first time that we actually saw fragments, right? Like I said before, you have one XCM message concatenated with another one. And actually, not Subscan and Polkaholic, which I saw some of the Polkaholic team there, they were not actually handling XCM fragments well also. And when we actually did this PR to fix this code to handle the fragments, we actually shared it with them so they could implement it in their solutions as well. And so this is pretty cool because there were 2 XCM messages on the same block. The first one was being executed correctly, but the second one was failing. And this tool allowed us to understand why the second one was failing, right? So when we run this code, you can actually see that the first message is telling you, hey, the hash of the fragment 1 is this one. And you can see that that's the hash of the event here, and everything went well. Everything was OK. But then the second message with this hash, you can see that it matches the Polkadot.js apps events. Actually has a fail to transact asset. And then we could actually see the instructions and understand what's going on. And actually, it was a lot harder to debug than just like showing this. But basically, we noticed that it was inside of the transact that they were passing. It was through the parachain staking palette. And we actually found the bug through another way. But this helped quite a lot to understand what type of interaction they were doing, what inputs they were providing, and so on. So yeah, this tool, like I said, if you're starting to work with XCM, it provides a lot of value into understanding how you can debug these messages and so. And you can see that it's very generic. You can use it with any. I provided Moonbeam specific examples, but if you put any WebSocket endpoint there, it will work as well. So I do have 5 minutes. So this is not a thank you slide because I have 5 minutes. I have multiple thank you slides, but I'm going to quickly go through the Moonbeam XCM SDK. So the XCM SDK, it's a tool to make life easier for developers, right? It abstracts a lot of the complexities, and a lot of them I actually mentioned before. Units per second, the developers only really need to understand what units per second are. Incorrect weight, Jesus, what weight do I have to provide for the XCM message? Multi-location what? I mean, what does it mean, a multi-location? For example, we deal a lot with Ethereum developers, and they don't really understand all these terms, and imagine to have to explain it to each single one of them. So the idea of the SDK is like, buddy, forget about all this. If you use the XCM, it's going to have some stuff pre-configured for you, so you don't have to worry about all these complexities that XCM brings along. It provides a very clean interface to get asset information like a parachain, palette, instance, general key. All this is baked into the SDK, so you don't have to worry about this. And it provides each parachain can configure their own stuff, so that in the future it would be ideal for I don't know, we have Alberto parachain. I can go into the SDK repo and just configure the Alberto configuration for the XCM SDK. So I'll briefly go into the example of how you can use it. And so basically the first thing that you have to do is initialize the SDK. You can provide an Ethers signer or an Ethereum signer, because remember that on Moonbeam you will be signing with ECDSA keys or Ethereum keys. But it also supports for a Polkadot signer, because if you're bringing DOT from Polkadot to Moonbeam, you will sign the transaction with, for example, the Polkadot.js extension, Nova Talisman, or whatever other wallet that you use. The SDK, once you've initialized it, you can, for example, log the symbols just to see the tokens that are supported. You can also get more information on each asset by, doing moonbeam.assets, and you'll find a lot of information. You can have information about the Glimmer native token in the case of Moonbeam. You can have the same for Moonriver, and so on with the different methods. I think I put it on the previous slide, but you can find more information on our documentation site for sure. It's in the case that we want to deposit an asset to Moonbeam, right? So this is bringing, for example, dots from Polkadot to Moonbeam. You can actually import the chain key and asset symbol. In this case, you want to say, hey, out of the asset symbol, I want to grab the dot. Out of the chain key, I want to grab Polkadot. This is basically where all the configuration is put in. And then let's say you want to do, hey, I want to deposit to Moonbeam, I want to deposit the dot asset, right? So the SDK underneath is doing all this complex stuff just to make sure that you as a developer don't have to really worry about all these complexities. And basically, when you do this Moonbeam.deposit, you're going to get the chains object with a lot of information if you want to check it out, but also a from function that you can use it's shown here saying, hey, I want to deposit dot from Polkadot. And then you can get sort of the Moonbeam address that you want to deposit it to, and then the Polkadot keyring, which is basically the key that you want to use to sign it, and so on. And then this function right here provides a lot of stuff, including the send function, right? And all these stuff that you see there, asset, source balance, source, and min, you can actually use it to check the logic of the transfer, right? I want to check if it has enough balance, if it has enough balance to cover the fees, and so on. I mean, this is very custom to every application, to each application. But the beauty of it is at the end, all you have to do is send the amount, and then you have an event, right? And believe me that's a lot simpler than trying to craft this manually with the Polkadot.js API or on Polkadot.js apps. And so this is the idea of the SDK. I'm not going to go through the example of withdrawals, but it's very, very similar, and it's on the slides if you want to check it out later. But it's, like I said, it's fairly similar. But the SDK just does have a lot of limitations that we hope that we can work through them. For example, it is very Moonbeam specific. So if you're a parachain that it's interacting with Moonbeam, you can use it, but it doesn't work for two parachains, for example, that are not Moonbeam. We understand that this is a limitation because the idea is to bring these tools to make it generic for that any team can use it. We also want to, right now it's only limited to token transfers, which is exciting, but at the same time it's a little bit boring because we want to do more interesting stuff. And so we want to add the possibility to also transact with other chains. And in the future, and this is me, I'm not saying when, this is just me, hopefully, that this will be part of the XCM SDK, bring the functionality of remote EVM calls so that you can do it in an easier way, right? Because it's not something that it's that easy to craft. So hopefully that it's something that it's in the SDK in the future. So I won't have time to go to the remote EVM calls, but it's on the slides, and I did a demo earlier on. So I mean, hopefully this was interesting for you guys. If you want to learn more about Moonbeam, you can check our website. Our documentation site has a lot of the content that I presented today. Check us in Telegram, Discord. You can contact us through there. This is a QR code for the presentation today. It's also very easy because it's at Moonbeam Sub0 2022. I'll be around for a couple minutes after the presentation if you have any particular questions, because I think I ran out of time, but it's your call. So thank you very much.